Hi, this is Mrs. Brobel. This is Chapter 14, Mixtures and Solutions, Part 4. So in previous videos, we talked about types of solutions, types of mixtures. We've looked at concentration, we've looked at solubility or solvation, and today we're going to look at colligative properties. I have here a jar or glass of ice, and I had added some salt to it. And the amazing thing in a short period of time is this ice is actually forming liquid because of the salt, and this is due to colligative properties. So notice that with colligative properties, we're not looking at what the identity of the solute is, we're just looking at the number of particles. So with colligative property, we're looking at how much is being dissolved, and at its dissolved state, it's actually affecting the property of the liquid. Ionic compounds, we know in the past, are electrolytes because they dissociate into ions and they, as a result, conduct electricity. Just to let you know, there are some molecular compounds that can mimic this situation. Okay, so with colligative properties, we could actually add a solute to a solvent and it lowers the vapor pressure. So the solute will actually cause the solvent to not have as much gaseous atoms or molecules above the liquid. And I'll show you a picture of that in a minute here. So please note that the solute is causing fewer particles to enter the gaseous state. Now, if you have a lot of solute or a lot of particles that are added to the solvent, you will have an increase in the vapor pressure lowering. And like I said in the beginning here, this is a colligative property of solutions. So if you add sugar to water, sugar is going to lower the amount of gaseous water molecules that are above the liquid. So here is a container that has just pure water on the left, and notice that the moment you add sugar to it, you have less water molecules that are above the liquid. So this is what we call vapor pressure lowering. Okay, we could have what we call boiling point elevation. So boiling point elevation is a little bit different than vapor pressure lowering. However, we're looking at a non-volatile solute, so something that is going to stay in the solid form. And with with boiling point elevation, what's happening is we're actually raising the temperature that a liquid would boil at. A lot of people think that you're adding salt to water when you're boiling pasta to make it boil faster, and that's not the case. What you're doing is you're actually elevating the boiling point of the water. And you may notice that your pasta cooks better at a higher temperature than it would at just 100 degrees C. So that's why you're adding salt to the water. So please note that with boiling point elevation, we're looking at adding extra heat, and that extra heat is obviously causing the boiling point to increase, and that's because you're raising vapor pressure of the liquid. Okay, and we'll do some calculations in class where we're looking at boiling point elevation. So we're going to use this formula here, delta TB equals Km. And notice that delta TB is the boiling point elevation. You're going to subtract, before solute with solute. And Kb will be given to you, and that's what we call a molal boiling point constant. Okay, so that'll be something that's supplied to you. And then lastly, M is molality. So M is not mass, it's molality. Now don't worry, you don't have to calculate molality, you'll just be given molality. Okay, here we have a series of substances or solvents that have different elevation constants. So notice that water, it's only a 0.5 boiling point constant versus benzene, carbon tetrachloride, ethanol, and chloroform. By the way, these are more volatile, so they have more gaseous molecules than water would. Okay, so freezing point depression. In my glass that was full of ice and salt, and I've got a lot of liquid here at the bottom now, this is what we call freezing point depression. So with freezing point depression, and this is the reason why they salt sidewalks and highways, is we're actually causing a lowering of the freezing point. So here, when you add particles to a substance, the attractive forces weaken. So here we have water molecules, and this is a dynamic system. So notice that an ice cube actually fluctuates between ice and liquid water. It's not all one way. The moment you add a solute, and solute typically is in the form of salt, notice that you're slowing down the process of going from ice to liquid back to ice. So there's more molecules that are in the liquid phase than they are the solid phase. And that's the reason why we get the freezing point depression. So notice that the freezing point of a solution, when you have a solute added to it, it's always going to be lower than that with a pure solvent. So that's what this diagram shows you here, is the normal freezing point of water is at this temperature, but the moment you add a solute, it actually decreases. And if you look at the boiling point, a pure solvent, the boiling point is lower than the boiling point when you add a solute. So a solution's freezing point, you're going to use the same type of calculation here. The only difference is we're talking about freezing point. So you'll be given a constant and a molality, and you'll figure out what's the difference in the freezing point depression.